Then I think we're ready to start. Some of us are. Ish, yeah. See some faces. Wait a minute. Is this the end of the year that's going on right now? Fatigue, relativity, saturation, these things. It's a week 6 thing. Well, there's a silver lining. That also means I only get to squeeze in the less amount of information before everybody can go to their Christmas recesses. Yeah, indeed, it's the last week, and we're going to talk about, well, there's much more to say about relativity, but I think we have the core basics, because in the first few weeks what we did, of course, is that we found what are the rules of space and time under what assumptions. We've done quite some practice with that. We've introduced a graphical way of introducing it by Minkowski diagrams. Last week we started by saying, okay, but what if you start interacting with nature instead of just looking at things flying around and exploding and these things? But if you start being part of that nature yourself, how does that work? Well, as you will remember from last week, that comes to 2 steps. Last step was that we simply introduced the expressions for energy and momentum. We did those in 2 parts. Or 2 ways. One of them was directly from the Minkowski line element, and the other one was using Lagrangian methods. And I hope in the course of the main lecture and the tutorials that the Lagrangian method does come with many, many advantages. Maybe the most important one being that one gets the energies and the momenta and the conservation rules all in one go. And that's an enormous advantage of that method. But what we have not done yet is introduce interaction, so to say. And it's important because it's very difficult to walk through Minkowski space-time without interacting with something. Yes? In fact, Bert and I are going to go bowling tonight. No joke, true story. Our department has, at the end of the year, some outing, and this year's winter outing is we're going to go bowling. That means I suck at it. I can calculate how the thing should go, I just have no idea how to make it actually go. This is why people like us do theoretical physics, so we just have to calculate how this works. But I mean, bowling clearly is an example of you interacting, right? I mean, you throw the ball, you give it its velocity, and you have to make sure that it adheres with the laws of physics. So, that's what we're going to do. We're going to introduce today the interaction to the whole story. And then, as a result, just laying out the learning goals for today, we're going to find why you cannot go faster than light. That's one of the key results that we're going to see today. We've already seen hints of that, why one cannot go faster than light, having to do with the gamma factor itself becomes imaginary. That might be problematic. You will find that the light barrier in the Minkowski diagrams we've spoken about cannot be crossed from either side. So there seems to be something going on with that speed of light, but we haven't quite formally proven yet that one cannot go faster than light, or if one can, under what conditions. So that's what we're going to get as a result. So long story short, 2 learning goals. We're going to extend the Lagrangian formalism such that they will also include interactions, and as a key result of that we will find Newton's second law, so to say, in relativistic form, including the proof why masses cannot go faster than light. So that's the plan for today. With that, let's immediately jump in. Let me first write down some key results of last week. We found in more than one way this equation over here. So this is just a repeat of last week. The relationship between energy and momentum of a single particle m. By the way, when I say particle, I don't necessarily mean the particles that people in particle physics study, like protons or something like that. I mean, it could also be a bowling ball or a spaceship. Yes, just something with a mass, and just I have to call these things particles. Okay, we found this. What we also found is that the expression for energy itself is gamma mc squared, and we found that the momentum is gamma mv. And if you go to low velocities, and by low I mean compared to the speed of light, then with good approximation this becomes 1/2 mv squared, the kinetic energy that one knows from Newtonian physics, and this guy becomes, by good approximation, m times v, the momentum as you know it from Newtonian physics. So there's that. Yes. There's also the plus mc squared here. But as we discussed last week, constant extra terms in Newtonian physics to the energy are of no concern, because one gets forces from taking the derivative of energies, and derivatives do not care about constants. It's another way of saying that where the 0 point of energy is up to human convention. So for all practical purposes, you can ignore this. In Newtonian physics, over here you cannot, in this expression. By the way, this is where atomic bombs come from, amongst other places. The fact that one can turn mass into an energy, that is because this M appears. That's why you can get nuclear energy from particles, right? The total mass of after a collision is smaller than it was before. That means energy was released, and by huge amounts, because the mass that you lose gets multiplied with c squared, and that adds up very quickly. Okay. All right. Oh, again, all of this is just a repeat of last week, and also the repeat of last week was you can get this from the Minkowski line element by playing around with the invariants that we know that exist in the theory, but one can also get it from the Lagrangian, and without going through the whole derivation again, the Lagrangian in relativity is given by this expression here, minus mc squared over gamma. In my tutorials, I don't know if it came up in Brecht's, but in my tutorials we had a little bit of a discussion on why the mc squared should be there. In the main lecture I just said, yeah, because it has to have an energy, the unit of an energy. There's a little bit more to it. You might remember that from the Lagrangian formulation, as far as the physics is concerned, it doesn't matter if you multiply Lagrangian with a number, 5 or 5 million or minus pi or so. Why? Because it drops out of your calculation. Which calculation? The Euler-Lagrange equation. dl dx equals ddt dl dv. That's the Euler-Lagrange equation. But it's just a combination of derivatives, and derivatives do not care about overall constants, so it always drops out. That means that this number, whatever you plug there, is completely irrelevant to whatever comes out of this equation, meaning you get the same laws of physics no matter what constant you put there. So of all the constants we could have put there, what we're not allowed to do is put a constant that is itself not invariant. If you're going to put a constant there that is not invariant, then unfortunately you find yourself with laws of physics coming out of here that are not the same in all inertial systems. But you want relativity to hold in all, that's the principle of relativity. So you're allowed to put a constant here as long as the constant itself is invariant. Unless we get a catalog of invariants, m is invariant, c is invariant, so that works. Then why mc squared and not m to the 17 and c to the 5? It's because the resulting energy that you get from it, from a Lagrangian, that's this object, changes value if you're going to make this by a constant. If you multiply it with 1000, then you have 1000 here and 1000 there, energy goes up by 1000, by a factor of 1000. Is that bad? Not really. But in Newtonian physics, we already had a convention for energies. And if we want our Newtonian, or excuse me, our relativistic mechanics to also have the same convention as that we have in Newtonian physics, we don't put 1000 here but mc squared, because then you get beautifully these expressions here. So the constant that we put there is not so much an issue as far as the laws of physics is concerned, but we do choose it such that if you go back to Newtonian physics, they nicely match up with each other. That our human convention for that constant agrees with the human convention that people did when they derived normal mechanics. So that's why we have a minus mc squared there. There's not much more to it. Okay, I think this summarizes last week's lecture. All right. But this, all of this that we did is for non-interacting particles, non-interacting masses. But is there any way that we can see this from what we have on the board now, that this is for non-interactions? I mean, I'm telling you, I told you also last week, this is if particles are left alone. But is there a way that you can see this from what we have? Yes?
Just a single mass?
That is a good point. there's a single mass. And usually if in interaction there must be some other object floating around that doesn't pushing or pulling or something like that. And that thing probably has a mass. Or it could be light and it doesn't have a mass, but there should be at least something else, right? So if I'm stealing your idea, the fact that our Lagrangian only contains the information of one thingy, namely the one particle, means, well, where's the interaction then? Where's the other stuff that it's talking to? That part is missing. Actually, that is pretty good. But maybe there's more. Yes?
Everything is with constant velocity?
Yes, that is another way of saying the same thing. By the way, both of you are completely right, but it's a nice addition. If you plug this Lagrangian into this Euler-Lagrange equation, then what you will get is that, first of all, that this is 0, because our Lagrangian doesn't depend on x. The LdV is not 0, in fact it comes out as gamma mv, if you do the math. There's still ddt, but because this side is 0, that thing must be 0. And between the brackets here you will recognize the relativistic momentum. So if we take our Lagrangian, plug it in there, you will see that we find ourselves with a piece of physics where that one mass is going with constant velocity. Right? Or I should say with constant momentum. But here's the expression for momentum, and you can play around with that and you'll find that the only way to make this constant is by having v constant. That's a cool little exercise. So already from the results we can indeed see, well, we have something moving with constant velocity. Well, that means nothing is doing any pushing or pulling. So we're missing interaction at this moment. Yes. So that's one. That's the second way you can see something is missing still. And it's good. It's fine. I told you we're going to do this in 2 steps. One without, and this week with. So the only thing we have to worry about now is, okay, well, where are we going to get our interaction from? Because then this Lagrangian apparently is not enough. But here's another, so if you want, this is the non-interacting Lagrangian for this one particle. So we have to build in our interaction, so to say. Now, how does one do that? Well, first, it's a nice observation that Lagrangians stack. If you have one Lagrangian for one piece of physics, it's a flying particle, and suppose that from other sources you have a Lagrangian for another piece of physics, maybe the other particle, or the electromagnetic field, or what have you. And you have 2 Lagrangians, and you can add them together. And you get a total Lagrangian of the bigger system, of both of these thingies. This is already apparent from the Euler-Lagrange equation because it consists of derivatives. And if we're going to put in a sum of Lagrangians, then the derivative applies on each of them individually. That's what derivatives do. The derivative of a sum is the sum of the derivatives. So from the linearity, so to say, of this equation, you can tell that you're allowed to just take one Lagrangian and add another Lagrangian, another one, as many parts of physics as you want to take into account. So, what you can do is that you add another Lagrangian, L2 or so, for whatever other parts of physics you're interested in. But then we're still not there. Because this might be maybe the other particle that's flying around, but they're still not interacting. If I make this the Lagrangian of yet another particle, then the Euler-Lagrange equation will just split up. Again, that's the linearity of the Euler-Lagrange equation. You just have one of the thingies and its rules, and the other set of thingies and their rules, with no interaction whatsoever. Yes? L equal to L1 plus L2. Plug in there is going to give you one equation for only L1 and one equation only for L2, and then each individually has to be 0. That's just another way of saying each particle is doing its own thing. But we want interaction. So, if you want interaction, you have no choice but to not just add the L2 of the other part of physics, but to add yet another part of the Lagrangian that contains both, where they combine. That's what you have to do there. And this is quite literally and now I do mean particle as in particle physics, what in particle physics we call the interaction Lagrangian. The part that says not just how each particle is doing individually, but how they talk to each other. So let's make it a little more explicit. Let's make this one particle 1, x1, and its corresponding velocity, and maybe there's a particle 2, x2, v2. Again, this part, no interaction yet. And this interacting Lagrangian, and it must of course depend on all of these variables. This one here. And a little bit more to it too. Right? I mean, the fact that it depends on all of them now, that gives it already some hints of interaction. But I also know it has to be products of some sort. Because every sum that I try to create is going to be split up here again, and you have two individual ones, individually 0, no interaction again. So your interaction Lagrangian must always be some combination of products of the individual constituents of your system. All of this simply by looking at your Lagrange equation. We haven't gone into detail yet. When I say product, there's more complicated constructs. And for the people in the know, if this is not you, don't worry about it. But things like contractions and tensor sums and tensor products, these things have to be built in. But just a simple normal something plus something will not do. Okay. So, how are we going to build in interactions with the rest of the universe? Well, first of all, we have to introduce the rest of the universe individually plus their interaction. That's my message here. So, let's do this immediately. Because, how can we do this? Well, let's take our Lagrangian here, and I'm going to add this interacting term. This interacting term I'm going to call minus capital V, which might make you think of the potential energy. It is. You don't know it yet. Okay. Potential energy you might know from Newtonian physics, but right now I'm simply saying, how does that work? Who of these people looks like me? Let's not go there. How long was this happening?
Just now.
Just now? Okay. I don't know. We'll work it out. It's this thing that these AI, so it needs more and more training. Maybe after 5 years or so, it will recognize me and not you. Who knows? I'm completely out of the sentence. What was I saying?
Potential.
Potential. Energy? Yes. Yes, it's potential energy. You don't know it yet, we will see. Okay. Now, potential energy in classical mechanics, non-relativistic mechanics, simply means your mass feels the rest of the world. It could be by other particles, it could be electromagnetic fields, it could be by feeling a force because it's tied to a spring or something like that. That's up to what this thing looks like. But here's the thing though. Whatever we're going to plug in, I'm going to only make it a function of x itself and not of v at this point. I'm going to introduce it later. So this interaction term, so how is this one particle feeling the rest of the universe, I'm going to make dependent on where that particle is. Not how much it is flying, again, that's a nuance point I will come back to later. I hope that already feels okay-ish for you guys, because if particles are feeling forces, something is pushing and pulling on them, that push and pull is probably going to be different at different locations. The spring is going to make you feel different if you pull it out more than if you pull it out less. Makes it x dependent. If it's a gravitational field, that means closer to the center of gravity, you're going to feel more than if you're far away from it. If it would be a constant, so it's not dependent on x at all, then our Lagrange equation is going to kill it. Meaning you won't even feel that there's something pushing and pulling. So again, from our Lagrange equation alone and simply from examples, so to say, you will know, well, it cannot be a constant, it has to be something that depends on position. And again, maybe also on velocity. To be found. Let's see what we get. Note that I'm not plugging in what the V is, it's simply saying some interaction term is needed, it must at least be x dependent. And let's see what our Lagrangian gives us. So this is our interaction term. Well, yeah, let's plug it in. Let's plug it in here. For Lagrange equation, see what you will get. Right? This should be easy to you now, Pavlovian. If somebody gives you a Lagrangian, you can immediately calculate two things. One of them is what is nature doing? That's minimizing the action, see last week, in other words, that's solving this equation. And the other one is, okay, what is the energy of the total system? And the energy of the total system, that comes from this equation here. So let's do both. Let's plug it into the above one and see what you will get. So let's plug it into the Euler-Lagrange equation. Again, this is us minimizing the action. For the people not in the know, I posted my written proof of this equation on Canvas last week Tuesday. Don't memorize it, it's not for you to know by heart, but if you're interested in why this minimizes the action, I wrote down the proof. Okay, let's plug it in and see what happens. Should be an easy exercise. Yes? Because this part, I already know what comes out. This. Or I should say, that's this part. This part, because it only contains the derivative with respect to v, will completely ignore this, because it doesn't depend on x, by assumption at this moment. Again, the velocity dependence I will plug in later. So this guy will only be affected by that, and this gave us this, dp dt. So I will get dp dt, and now I do mean relativistic momentum, this one. But it's not zero anymore, because the zero came about because Euler-Lagrange says that we have to take the derivative of the total Lagrangian with respect to x. And as opposed to last week, we now do have an x-dependent part. It's minus v of x, whatever v is. So I will get dp dt is minus dv dx. This gets replaced by that. Yes. And note, I'll come back to your point. Note, it's not zero anymore. That means we actually do have this interaction that we're looking for. Particles will not go with constant velocity because there's something doing some pushing and pulling. We can make it more explicit because dp dt, if we were in the lucky situation of constant mass, then this would be, let's go to slow velocities. Right? V is very small compared to the speed of light, so gamma is pretty much 1, just as an example. Then this becomes m times v with a constant m. This turns into m times a. And the other side is minus the position derivative of this capital V. And since we know that in this regime we should have gotten m times a equals f, that means apparently these two things are the same. And that justifies calling that thing a potential energy, capital V. Because if you know your classical mechanics, your non-relativistic mechanics, Kerko, or here before Ronald Westra told you that the derivative of a potential energy minus is what you call the force. That's how force and potential energies are related. So from this observation alone, I know that this is not just any interaction term, it literally is the potential energy. Simply by going to the regime that we know, low velocity Newtonian mechanics. And of course, that's why I called it capital V to begin with. Yes. Okay, so Euler-Lagrange now tells us, at least in the regime that we know, that we're going to get Newton's second law. And this is for the case when you have low velocities. If you don't have low velocities, so you don't get to make this approximation, then this is our relativistic version, if you will, of Newton's second law. That's what we've now found. What it looks like is dependent on what V is, your potential energy. In that sense, we're not in a different field than we are in classical mechanics, where the V also has to be supplied from the outside, but here we are. So, there you go. Here's where some people worry sometimes. That is, wait a minute. That means that the particle, the mass, will now accelerate. But accelerations are not allowed in special relativity. See at least one person make a face. The scowl. So, am I wrong here? I mean, I get an acceleration or something that allows an acceleration, but in special relativity only talk about constant velocities? Scowling face.
Things can accelerate as long as the frame itself isn't accelerating.
Exactly, that's the well. Oh. Yeah.
Okay.
Yes.
We're in an inertial reference.
Yes. Okay. Thank you. Yes. The thing is that you look at are particles are completely allowed to accelerate, even if you start touching and pushing and pulling on it, as long as you, as the observer, are yourself in an inertial frame. And this is where I stopped you, because I said if your frame itself is not accelerating, wait. You don't know whether your frame is accelerating. You're accelerating always with respect to somebody. Yes? So this is why all the way back in week 1 we defined an inertial frame not by its relative acceleration with respect to something else, but by Newton's first law. But outside of that, okay, 90% in, all good. Okay, here we are. So no problem there. Okay, but we can work this out a little bit more though. Because you can plug in our value for P, that's this one that we already found last week in these two ways. Plug it back into there, and then you get to take this time derivative. Well, that's a little crappy because there's a V at least in 2 places in your P. It's here, but it's also buried in the gamma. So yeah, take some derivative taking. Should not be your biggest problem in life. But at some point, if you've gone through the calculation, you will find that the left-hand side, by derivative taking alone, becomes gamma to the 3, n times a, where a is the xdt. Trust me on this, or take a nice 10 minutes and work this out. It's literally just derivative taking. I'm not plugging any new physics in. It's a gamma to the 3. So I cannot help myself. Has to do with the product rule. Because the product rule tells you to take this guy's derivative, but gamma is a 1 over square root, and the derivative of 1 over square root is 1 over the square root to the 3rd power. That's derivative taking. So already from the product rule, where the first term applies only on the gamma, you're going to get a gamma to the 3. And then by product rule, you get an additional term, do some algebraic cleanup, you end up over there. That's where the gamma to the 3 comes from. And the other side, again, is, sure, it's minus the potential energy's derivative with respect to position. Let's call that by its name, the force. This, if you will, is Newton's second law in relativistic mechanics. This is how you interact with the particle. If you want to accelerate a particle, do the exact same thing as you would in Newtonian physics, and start pushing and pulling on it. By whatever means. By your own force, by like magnetic fields, take your choice. Maybe gravity even, non-relativistic gravity, maybe by ropes, etc. And then you simply solve this equation. This is usually, not always, itself a function of x. And then you have to solve this equation. And if you do that, we're now in mechanical situations, you will end up with x of t equals something. Yes? What that something is of course dependent on f and its dependence on x. Yes? So that's context dependent. Here's the bad news. It's an extremely crappy calculation to do. And the reason is that, well, this is a differential equation. I mean, if you want to know where the particle is at any moment in time, then what we have here is, well, let's bring the m to the other side. Then you have second derivative of x with respect to time divided by 1 minus the first derivative with respect to time squared divided by c squared, and of that you take the 3 over 2 power. equals f, and if you're lucky, that f itself depends on x. So here's a crappy differential equation. There's an unknown x of t, and it must be such that if you take two derivatives and divide it by the cube of the square root of 1 minus the first derivative squared, it must equal something with an x itself. That's a very crappy differential equation, unfortunately. Yes? So that sucks. And there's nothing we can do about it. It has nothing to do with, well, nature's pushing and pulling in a difficult way. The crappiness, the fact that the thing you're looking for appears in its own derivatives to crappy powers, is a result of this side of the equation, and that side of the equation came from here, and that came from there, and that came from the Minkowski line element. It's space-time itself that's making your life difficult. It's not the pushing and pulling. And there's nothing you can do about it. It makes it just more complicated. So that sucks. Don't blame the messenger, but here we go. By the way, there's a silly equation, general relativity. It's literally simpler than this one. Yes. But in principle, this can be solved, yes? So you might have to do this numerically or by other means, but in principle, this can be done. Okay, well. Let's prove that from this result, it is impossible to go faster than light. This mass cannot be accelerated faster than light. That's my claim. And I'm going to make this claim independent of how much pushing and pulling one does and how long you do it. And usually if you have a particle, you start pulling on it, it accelerates, and if you pull long enough, it will accelerate more, and the velocity will go up, 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 and at some point, if you pull long enough or strongly enough, it will go past the speed of light. There's nothing about the original Newton's second law that prevents that from happening. But here there is, and I can prove that right now. Let's go back to this version of the equation. There you go. That's that thing. And let's slightly rewrite it. Oh, by the way, there should have been a 1 over n there. Brought it into the other side. Let's rewrite it slightly. What I have here then is that the acceleration, when brought to the other side, is f over m 1 over gamma to the 3. Same equation, written differently. No problem, because if I divided both sides by n and by gamma, but m is not 0 by assumption, and gamma is never 0. So I can easily divide this on both sides. Let's rewrite it still. Same equation, just the gamma written out. And I can now ask myself the question, what is the fastest my particle can go? And if you recall your calculus, if you just want to know what the highest value is that something can obtain, you have to look for when the derivative is 0. So if I'm interested in knowing, well, what is the highest velocity one can obtain, I have to take its derivative and find its 0 point, so to say. So highest velocity is obtained when the acceleration has become 0. It's quite obvious, yes? I mean, if it doesn't accelerate anymore, you don't add more speed. Well, here's the acceleration. And the highest velocity is when this is 0 by definition of highest velocity. Well, the force is not 0. And again that direction. It would have thought it easier if it was you, but
No, I'm not in
no, I know. So it really it doesn't. Yeah, there you go. Okay, keep me updated on this, yes, especially that row, because for some reason the thing likes to see you guys. The highest velocity when this whole thing is 0. Well, the force is not 0. Right, back to my premise. Something is doing pushing and pulling. Well, m is not infinity. So the only thing in order to get highest velocity is to make this guy 0. And when is that the case? Well, that is when v is. When v equals c. If you want this to be 0, then this must be 0. And that's another way of saying that the highest velocity that one can obtain is c. So no statements about, oh, the amount of kilograms goes up if you go faster and that's your problem. No, masses stay the same. It's this guy that's thwarting your higher velocities. And note that this is true, this conclusion, regardless of what f was, as long as it's not 0 by itself already. If it is 0, then the whole exercise is moot. Because this 0 can never, ever, ever, right, I mean, multiplying whatever it is always going to make 0. So this statement is true regardless of f. It's also regardless of how long you're doing the pushing and pulling. So here you go. Here's one proof why masses, by mechanical means, by pushing and pulling, can never be made to go faster than the speed of light, no matter what f was and how long f has been acting. There's that. Is there an exception to this rule that you can tell from the equation?
When mass is
Yeah, when this is 0. Well, what if this 0 is exactly compensated by the 0 in the denominator, so to say, right? So they cross out. Don't let mathematicians in the room, they worry about these things. So they're just more sloppy. At least it opens the possibility. I'm not saying that therefore it's true, but there's at least a possibility that if you make m also 0, then this doesn't hold anymore, or the equation might hold again. So this is 0, but that is 0, and sort of the zeros cancel out, and then the acceleration might still be bigger. That doesn't work, unfortunately. So, I mean, mathematically that's a true statement, but all of this from here to here going back down is assuming that mass is not 0. If mass was 0 to begin with, there was no derivative to be taken to begin with, and the whole equation, the whole set of steps would not have worked. Yes? So, yeah, the only thing that could potentially have saved us is to take massless particles, but if massless particles were the case, then from here to here, exactly from there to there would not have worked, and the rest would not work either. So, from there to there, we restrict ourselves to massive particles, even if they're low mass, as long as it's not 0, and then we're here, and then you see that there's absolutely no way to circumvent this. So that's one way of seeing that the speed of light cannot be exceeded by pushing and pulling. What about massless particles, though? Because we know that at least some massless particles go actually with the speed of light. Again, this doesn't apply anymore. Any ideas what to do from all the information on the board? No one? Is it weak 16 or a difficult question thing? Lack of coffee thing? Combination of their nodding faces. Well, that means that our description of nature cannot be complete right now, because what we have at that side of the barrier here will only apply to massive particles, yes? Massive stuff that has kilograms. But we would also like to look at things in physics that do not have mass, like photons or gluons or what have you, so on and so forth. So we have to do something else for those. Let's make a little extra block here. Because forces, in the Newtonian sense of the word, do not apply to masses at all, or to non-masses. Forces are things that operate on masses. So it means, again, all of that is not true, but energies do apply to those systems. So if you want to look at massless situations, then what one has to do is look at the energies of a system. This already came up in some discussions outside of the any lecture. But if you have a massless particle and you go to this equation, and remember this one we got from the Minkowski line element. The Minkowski line element doesn't know about mass or non-mass. So this should hold for all systems. Now, so we are allowed to take that one and just plug in m is 0. Then you find that E equals P times C. Energy momentum pretty much the same thing, up to a C if you're a massless particle. You might at this moment worry a little bit because you might say, but wait a minute, P itself here contains an M, you're right, but so does E, yes? So you can cross out the M on all sides, so to say, if you so want. So what do? At the moment that we have massless particles, we simply define momentum as the energy divided by the speed of light. And this simply becomes a definitional thing. So massless situations have this, that the momentum is literally defined as that guy. And then you can still do your maths. Because you will remember that the energy of a system is conserved. In the tutorials we prove that for every situation. If this is true, then all of it is true. Right? You recall this? It's good to remember this, that we had that if you have a Lagrangian, and it depends on the position and the velocity, no matter what the thing otherwise looks like, energy will be conserved. So that's also the case if you have a system that doesn't have massive particles at all. Well, then you can simply define the momentum as this object, and then you can simply play your usual energy is conserved game and do your mechanics with that, without ever having to worry about forces of that. Now we can do a little bit more to it too, because the expression for energy, as we already saw, is gamma mc squared, which is mc squared 1 minus v over c squared, square root of that thing. And here we can play that game though. That we tried over there but didn't work. Here we said, well, what if mass is 0? Okay, didn't work here again because from this on out we were assuming mass was not 0, but in this expression you can actually quite literally see that if mass is 0, you would either get 0 energy, that means the thing doesn't quite exist. 0 energy simply means it doesn't have energy to interact with the rest of nature. Meaning it either doesn't exist or it exists but it doesn't do anything, which for physics is pretty much the same thing. Yes? Non-measurable thingies, for all practical purposes, do not exist. As in, you cannot measure them. So that option, unfortunately, flies out of the window, that you plug in m is 0 and leave it as that. But if at the same time v is 0, then you actually get 0 divided by 0, which in principle could not be 0 and could not be infinity. So this leaves open the possibility that yes, you can actually describe massless particles, but they have to go with the speed of light. There's no choice in the matter. And that's indeed what we observe in nature. Right? All massless particles that we know do indeed go with the speed of light. And it also works the other way around. If a particle goes with the speed of light, then E becomes infinity. Now think about what that happens. Or what that means. This energy is conserved for any system. We proved that last week. So if we would have a particle over here and we would make it interact with some environment to make it go, and go faster and go faster, then along the way, at some point it will go with very high velocity. But since energy is conserved, I get to just check the beginning energy and the end energy and see how much came from the outside, how much we put in. So if you want, the energy that the particle will have once it goes with velocity v is the energy that we from the outside world put in. So this is how you can read this equation. It's not just the energy of the particle, because conservation of energy is how much we from the outside world have to squeeze into it. But if v of the particle goes with the speed of light, then the energy is infinite. Meaning that we have to put in an infinite amount of energy to make the particle go with the speed of light. That's another way of saying why particles cannot go faster than light. It takes the rest of the universe an infinite amount of energy. Yes? So again, unless the particle did not have mass to begin with, because then the energy needed drops down again. Yes? This is why you don't have to put in energy if you want to make photons go, they already go. Long story short, the arrow goes both ways. If a particle has no mass, it will go with the speed of light. If a particle goes with the speed of light, it must have no mass. Those things are completely related in special relativity. You cannot separate these two from each other.
Clarification.
Yes.
It would take infinite energy for a massive particle.
Or from anywhere.
Anyway.
Yes.
But no, because if m is 0, then that's doesn't hold.
I'm simply saying that because we know that any Lagrangian of the type that we have been discussing since last week obeys the principle of conservation of energy, then it means that if a particle started with 0 energy and it ends up with an infinite amount, that's what you get. If m is not 0 but v goes with c, then that energy must have been supplied by the outside world. That's simply what I'm saying. And slightly relates back to what I was saying before, that the total Lagrangian is maybe the particles plus that of the outside world. Right? Remember, you can stack Lagrangians. But we proved already that any Lagrangian comes with the conserved energy. But if we find that the particle's Lagrangian and its energy becomes infinite, but you know that the total amount should be what you started with, that infinity from here must have come from that part. That's simply what I'm saying. The energy came from someplace else. Now ask Marcel, who teaches particle physics course, that this is true. He will confirm for the simple reason that they have to put an enormous amount of energy into the particles in the particle accelerator to make the particles go even close with to the speed of light. Yes, that's simply what you see happening here. Okay, so far so good. Because I now want to look a little bit more in detail about to these guys over here. Right now, every conclusion is simply based on the fact that there is some interaction Lagrangian going on. Potential energy, as we've now found that it is. The question is where it comes from, the potential energy, as in how do you know the expression? In our case, as we build it up over here, this potential energy is completely fine to be the potential energy that you might know from your Newtonian physics. Because look, we got this law, and if you slow down enough, then this guy goes away, and you actually do get Newtonian physics back. Simply telling you that the V was just the Newtonian energy that you had in all other contexts too. So, Dutch people, take your BNOS, take your potential energy that you know from classical physics, you can plug it in there, work it out. Yes? But there's a glaring mistake here somewhere on the board. And I'm waiting for somebody to notice it.
Should we bury it?
What's that, sir?
Invariant?
Ah, there's an invariance issue. Yes. But where's the, you're right. There's an invariance issue. You said it should be invariant. What is the it here?
Like the potential?
The potential need not be invariant. Or does it?
Or for the total Lagrangian to be invariant.
Well, Lagrangian never had to be invariant. This Lagrangian is not invariant. It also wasn't invariant last week. No, really. I mean, there's a V in there of the thing that you look at. And well, here's the thing. Its V is now 0 in my inertial frame. So its gamma is now 1. So in my frame, this guy, its Lagrangian, is minus mc squared. But look, I'm now moving to a different inertial frame, still looking at the same thing. It now has a velocity with respect to b. Gamma is not 1 anymore. That means the Lagrangian has changed value. Well, that's clearly the opposite of an invariant. Lagrangians never had to be invariant. Last week we saw that what needed to be invariant, marker, what needed to be invariant was not the Lagrangian, but the action. And the action is defined as this. And the whole point that we played last week was because dt is not invariant because of Lorentz transforms, then gamma is probably not invariant, but you have to choose the non-invariance of L such that it cancels the non-invariance of the dt, and that's how we find the 1 over gamma. And again, the m minus mc squared is just a matter of convention. So Lagrangians were never invariant to begin with, so that is not so much a problem. So you were completely right. There's an invariance issue, everything that we're doing right now. But it's not because the Lagrangian is not invariant, because it never was. But we're homing in on the problem. What's that, sorry?
Action has to be invariant?
Yes, the action, yes, that is true.
So the potential energy should also be invariant?
Not the potential energy. Remember, you plug in the L, and you multiply the L with the dt.
Oh, so the dt needs to be invariant, the dt?
Well, that's one way of doing it, to make the dt invariant. Fine. I'll go in a tangent in a moment about this one. Yeah, it's dangerous to ask me to go on a tangent, but there you go. No, I mean the dt, in the way that we've now written our Lagrangian, dt is not invariant. Yes. But L times, if dt is not invariant, then L times dt must be, and that means you have to choose your L such.
The Lagrangian of the potential energy, or the action of Lagrangian of the potential energy is not invariant?
So the action of the Lagrangian of the potential energy is not invariant. Okay, that's correct. Parse, but yeah, there we go. Now this is not invariant, but then again, this isn't either. But if you multiply this with t, dt, it's still not invariant. This one is. That's how we made it. We chose the gamma such that if you now multiply with dt, the whole thing becomes d tau, and the d tau is invariant. But this guy multiplied with the dt, as we should be doing here, does not make an invariant action. So we've broken one of the most sacred things in special relativity, namely the principle of relativity. That all inertial frames should give you the same results. And since we now have an action that doesn't have the same minimal value, that means the laws of physics are different in every frame. So, although mathematically all of this is correct, there is a problem.
Should it also depend on the velocity?
Yes, there was. You might remember that I was going to build in a nuance, and here's a good way of doing it. There's at least one way, or two ways, sorry, to solve the non-invariance, and let me be clear, not the non-invariance of the L, the non-invariance of S. Yes, there's two ways of solving it, maybe three. One of them is to never have written down a Lagrangian or an action with a dt, but have immediately started with a d tau. You could have done that too. And this is the tangent I will go on in a moment, because I'm tempted. Yes. But there's another way. Another way is that we simply don't care. Not really. I mean, yes, let's make the whole theory work in all inertial systems. But then again, usually if you throw a pen around or you start pushing and pulling up things, you usually do it from one particular frame. And in that particular frame, as long as you stay there, you don't care that in the other frame it doesn't quite work anymore using the same rules. Right? You're sort of limiting yourself from going to other inertial frames and just sticking to one. That's sort of the poor man's way of doing it, so to say. But that is how mostly we do it, I should say. That if you want to do relativistic mechanics, then we usually do solve this one with the mental note that it only works in that particular inertial system and not in any other. Okay, so that's a second way of solving it. Just sticking to one frame and not worry about the others. The third option is indeed to make V, this V, such that if you multiply it with dt, invariance is retained again. Yes? And here's Dutch people where the Venus runs into problem. For the non-Dutch people, Venus is a booklet that you get in high school that has all the formulas, so you don't have to memorize all those 5 formulas when you go into your exam. Okay? I'm not a Venus fan, as you can tell. Here's where Venus runs into problems. Because the potential energy of almost every system that you care about in mechanics only depends on x. But x, as you know by Lorentz transforms, is not the same value for everybody. That's where your non-invariance comes from. And you cannot solve that here, because if you have a v of x and you go to any other inertial frame, then Lorentz transform is going to change this x into something else. And that means you lose invariance. That's again this breaking the principle of relativity. And as long as there's only an x in there, it will not work. It will never work. Every x dependency you try to put in there is going to spoil your invariance of action simply by the Lorentz transforms all the way back in week 2. So it really means that this expression is always wrong. Right? If you want to make it work in every inertial system. Don't make it stop you using this formula. It simply means this formula is true within one frame. And if you only care about that one frame, you're still good. Yes, Max?
You said the first one that you were going to go, the first solution that you were going to go on a tangent about was making minimizing the action formula equal to d tau.
Yes.
I.e., you're making it not times dt, you're making it times d tau.
Yes. And tangent to follow.
Yeah.
If I allow myself the time for the proper time. Every v of x will not work here. If you want to go to everyone. So you better allow yourself to put in some extra terms there. Some extra dependencies. And those extra dependencies should be such that they work in conjunction in such a way that maybe you put a v in there or a t. Maybe you put a t in there. Okay? That if you then go to one inertial frame, then x changes by Lorentz transform, then t changes by Lorentz transform, but their combination stays the same. Oh, that is still not true because it's still multiplied with dt. That combined effort stays the same. Okay? You have to look for a particular potential energy to make that work, but in principle that's allowed. And here's that nuance that I spoke about before. You can also put in a velocity of a particle. Because particles' velocities are also going to be changing from inertial frame to inertial frame. That's the Einstein velocity addition rule. And maybe if you work hard, you can find a potential energy that depends on position, that Lorentz transforms, that depends on v, that also Einstein velocity transformation transforms, multiply it with dt, that Lorentz transforms, and the whole combined effort stays the same. Then we are back in inertial frames. Then the principle of relativity is saved. Yes? So, long story short, we can only save the principle of relativity here if our potential energies are going to depend on more than just x, either also on v, and maybe even on time itself. And again, that disqualifies many of the formulas that you might know from high school, except for one maybe. Does anyone happen to know a force that depends on velocity and on position? But actually, you don't count. You count in many ways, but not.
I remember I wrongly answered this question when I was doing special relativity.
This, what, 3 years ago? 4?
5, I think.
5. What was your wrong answer?
Your question was, is there a force that does not depend on velocity? And then I was like, oh, I know this force.
Okay.
And then I answered what should be the answer here.
Okay. Then let's give the audience time to get the correct answer to the wrong question.
Velocity and position.
Velocity and position, yes.
Lorentz force?
The Lorentz force is an example. Because the Lorentz force if you have a single flying particle in a magnetic field, the Lorentz force for that particle with a charge q is a magnetic field, cross product with the velocity times the charge. If you're not into electromagnetism, this is the force that a particle feels because it's flying through a magnetic field. And that force depends on how fast the particle is flying. That's your Lorentz force. But magnetic fields are not homogeneous. They look different at different positions. One of the Maxwell's equations tell you that magnetic forces cannot be straight. they always have to curl back into themselves. It's called Ampere's law, or Maxwell's second equation. So you know that this guy is x dependent. This is not an x, it's a cross product of multiplication. This is not your thing, vector calculus. Remove the vector part, put the sine of theta. The sine of theta is the angle between the velocity and the magnetic field. Okay? Point being, this guy is position dependent, because Maxwell's equations force them to. There's no homogeneous magnetic fields. But the force itself depends on how fast the particle is flying, and lo and behold, you have a force that is both dependent on v and on x. And what do you know? Nature has decided that this particular way of v and b is always such that when its potential energy plugged back into here, plugged back into there, is invariant. It's almost like a miracle. That there is a force in nature that has decided to be exactly such of x and v that all of this works out. Yes?
You also said that sometimes even depend on t.
Yes.
What is this sometimes?
Oh, that's again, it's context dependent. That could, for instance, be there's a particle flying around, and then you from the outside world is changing the magnetic field around.
Oh, okay.
Yes. But that would mean, by the way, that in the Lagrangian I have to add you in your interaction and your knob twisting. So yeah. This, by the way, I mean, I sort of make a joke out of this as well. That's a big coincidence. Well, it isn't. Because Maxwell's equations, let's go back all the way to week 1. Maxwell's equations is where Einstein got relativity from to begin with. Maxwell, going all the way back to week, or history-wise, but also in our course-wise, in week 1, we started with the Maxwell's equations, and I said, well, Einstein and other people noted that they have special properties. And what the special properties being that the speed of light had to be the same, had to be invariant, and from the invariance of the speed of light from the Maxwell's equations, we ultimately got the Lorentz transforms, we got the Minkowski line element, we got this, and all of this follows, then clearly what is going to come out is going to be in agreement with the Lorentz, with the Maxwell's equations. So it's not a coincidence at all. So here's a nice philosophical way of looking at the Lorentz force. Why has nature decided to make particles feel magnetic fields in this particular way? Because if it didn't, if nature, making it sound like she had it's a thinking agent, but you see the point. That because if nature had not adopted Maxwell's equations in exactly this way, relativity would not have been true. So if you want, Maxwell's equations and the Lorentz force had no choice but to look like this, because otherwise the principle of relativity would not have been true. Historically, we found it the other way around. We found Maxwell's equations, then later people found, oh, wait a minute, there's deeper principles at work. But if we would have known the deeper principle, if we would have started with the invariance of the principle of relativity, that every inertial frame should give you the same laws of physics, then actually, then we could have derived that the Lorentz force was this guy even before we ever measured it. The Lorentz force is what nature had to do to save the principle of relativity, so to say. That's a nice way of looking at the Lorentz force. I should also say that this is how Lorentz, the guy, the scientist, found the force. Some people say, oh, he measured it in a laboratory. He was a theoretical physicist. He never went near a laboratory. He was sitting in an office doing calculations. And he found, solving something very similar to this problem that we were doing here, he found that the force on particles when they fly through non-rest frames of a magnetic field better look like this in order to save the principle of relativity. That's why it's called the Lorentz force. It was only later that it was measured and he was right. So, there's a little piece, nice piece of history there. All other forces in nature, as in the ones that you know from your classical mechanics, do not work in this manner. It's literally the only force that has this property that we know of. Does that mean that no other interaction can be written in this way? Well, yes, pretty much. Yes. So, what are we going to do if you find yourself in a piece of nature where your formulas from the Binas do not work? Yes, but you do want the principle of relativity to be upheld. that's what I'm going to do next. By the way, most of our main message of today has now been done. You have your formulas now to calculate things in a non-inertial, still in an inertial frame, but when there's interaction. And the exercises of this week are simply applying this crappy formula and see what comes out. Yes? See what happens. Oh, and you will see in all cases the particles will never go with the speed of light, no matter how fast you try to move them about. Okay, so main message delivered. Let's remove this. The last part, so we have about 15-20 minutes left, are going to be a little bit more abstract. That means that there are also going to be some steps that I cannot fully prove on the spot. So please focus more on the concepts than on the mathematics. But for the people who are going to follow a course on this, you will see some more of the details there, yes? Okay. Question. In week 4 I uploaded a video on 4 vectors. I mentioned nobody has to memorize this, but it might help you connect to our courses. This is not testing you guys, but who has seen that video? Few people, yes? Again, if not, completely fine. Because I will use a little bit of that video right now. Yes? So I'm going to introduce a few concepts. If you want to know the proof, you either watch the video or forget about it at all. That's fine. In other courses it will come back, and if you're never going to do relativity again, you will never see it, you don't have to worry about it. I will connect things, because we are now open with a glaring question, because if we're going to finish the course right here, then we have a crappy situation that you can only use relativity in an interacting sense, if you're looking at the Lorentz force, or stick to one inertial frame and not worry about the others. And I want to give you the methodology to apply to every inertial system. But that requires me to dig a little deeper into the mathematics. So, here's the key part. Yeah, so this is the methodology, how one gets other situations. Go to the following. We're going to introduce an object, x with a Greek index mu. This is not x to the power mu. It's a label. Mu tells you which of the 4 space-time positions you happen to be looking at. Now, space-time positions in our work are either t, x, y, or z. So there's 4 of these things. And that by the mu we simply mean which of the 4 do we mean? Do we mean this one? Do we mean that one, or that one? X is mu, mu is 0, is by convention meant to be the time part. X is 1, 2, 3 are the spatial parts. Just like that. Okay. These is what we call together a 4 vector. This nomenclature. I'm simply saying let's group space-time coordinates, an event, into one big vector. That guy, his name is called the 4 vector. Now it's not a 4 vector because it's 4 numbers in a vector. It's because it has a special property. The property being that these 4 numbers have a very particular way of changing into different numbers if you go to a different inertial system. So let's go to the prime system. You're going to get 4 new numbers. And do you remember what the rule is? How t turns into a t prime and how x turns into an x prime and so on and so forth.
Lorentz.
That's the Lorentz transforms. That's what the Lorentz tensor will look like in a moment, but you're right. So, what do we have here? Let's focus ourselves on the spatial situation where the 2 frames are moving in x direction with respect to each other. That doesn't have to be the case. It's going to make the following mathematics a little bit easier. Yes. So, let's do a Lorentz transform. Week 2 to a different coordinate system, and that means what used to be t becomes t prime, what used to be x becomes x prime, and so on and so forth. And we know exactly how that works because t turns into gamma t minus x. I'm always struggling with the c's for reasons that we've discussed many times. This over c squared. There you go. X prime we also know how it transforms. It's x minus v. Oh, actually, this was correct. No, that was not correct. Like this. There you go. Right. Lorentz transforms, we derive these ourselves. And if you only transform in the two inertial systems are only in x direction, then y and z are left alone. Okay.
Why instead of prime?
Because they're the same number, but you're right. So let's, there's the same number, but let's be consistent. In the unprimed, it becomes this. And you can turn this, again, this, I'm just putting what you know already in slightly different words. But you can write this now in as a matrix multiplication. I'm turning this into linear algebra. I have to have a matrix such that if you multiply, it's a 4 by 4 matrix, and if you multiply these numbers with these numbers and the next one, then this turns into that. Then I simply have written the Lorentz transforms in terms of minus V over C. And I've simply turned the Lorentz transforms into a matrix multiplication. Excuse me, let me make a little bit more space. Minus gamma V over C squared. Then I have 0, 0, 0, 0, 1, 0, 1. This T, X, Y, Z. There you go. And this becomes minus gamma V. This is a plus gamma. And this is a 0, 0, 0, 0. There you go. There's your matrix that does the transformation for you. Yes. Again, just Lorentz transforms written as a matrix multiplication. And this guy is what we called originally x with a mu on top. 4 numbers just combined into one symbol where mu tells you which of the 4 symbols you want. Then this guy itself can be written as one single object. And we call that capital lambda. That's simply the matrix.
The Minkowski matrix.
That's indeed the Minkowski matrix. Oh no, careful. Yeah, matrix. Yes, but not to be confused with the. No, it's not Minkowski. It's a Lorentz. Almost right. It's called capital L. It's just another way of saying those 16 numbers combined. But just as over here we are being economic, that we say, hey, you know what? Instead of writing down 4 numbers all in one go, let's write down one number. And depending on the value of this mu is, 0, 1, 2, 3, you can select which of the 4 you're interested in. Well, we can do the same thing here with x mu prime. And the other side has this matrix in between. Now this matrix is the Lorentz matrix because it contains the Lorentz transform. Again, it's just 2-bit notation, but I promise you there will come a point, and from the point coming from this, you will be able to write down Lagrangians from now on that work in every inertial system, even if they come from the Beano, so to say. Yes? So this new notation is simply necessary for me to make my point about, well, how do you apply what we did before for all forces, and not just the ones that happen to be the Lorentz force. Okay, so some more notation still. If I were to write down the same thing with another Greek letter, nu in this case, I simply mean the same 4 numbers. Any Greek letter will do. It's simply labeling, 4 values. And whether you call this mu or lambda or something else, that's up to you. The only reason that we use different symbols is we might have expressions where we have one of these, but the thing appears twice, then you have to be sure that you pick the right one from the right one. Right? So we use a different label to distinguish them from each other. Here's a point, and here's where your Minkowski matrix will come. Okay? I'm going to introduce one more new symbol, eta. It too has Greek indices, labeling which of the numbers you mean, and note, because with two labels, it means there's 16 numbers now. Because mu can have 4 values, and nu can have 4 values, making for 16 possibilities. Matrix-wise, if you were to write it down, it's literally defined as -1, 0, 0, 0, 0, +1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. It's like the unit matrix except with one minus sign. This one is called the Minkowski matrix. Can somebody tell why it's called after Minkowski, this one? Is there a connection one can make with something that you've seen before, also named after Minkowski? The line element. The line element, remember, started with minus dt squared plus dx squared plus dy squared plus dz squared. So the Minkowski matrix, if you want, simply collects the coefficients in front of dx squared or dt squared, dx squared, dy squared, and dz squared. That's what the Minkowski matrix does. Again, notation, notation, notation. Don't do physics yet. Suppose that, by the way, let's check for a moment. Suppose that I say mu is 2 and nu is 3. Right, there's 60 numbers. Simply labeling. Mu can be 4 numbers, 0, 1, 2, 3. Nu can be 4 numbers, 0, 1, 2, 3. And I happen to be looking at mu is 2, nu is 3. Which of those numbers am I referring to now?
Mhm.
0, 1, 2, 3, 0, 1, 2, 3. I think I said 2, 3. Okay. 0, 1, 2. And then within that row, I take 0, 1, 2, 3. 0, 1, 2, 3, 0. So again, 60 numbers, and by assigning the right values, you can pick out those 60 numbers. Now the same thing here. If I say x mu, x0, I mean that one. If I mean x1, I mean x. If I mean x2, I mean 2, y, and I mean x3, I mean z. Now almost to my main point. Let's now do the following. Let's take the Minkowski matrix, multiply it with x mu, but I'm going to need 2 of these, so I better use different labels. I mean, it's the same 4 numbers, but the labeling goes different. And this simply means let mu run over all 3 values, and let nu also run over all 3 values. Yes. So this is 16 thingies adding together. You have to add all of them together. That's what the summation symbol says. So if you were to write this out, there's 16 terms. Something plus something plus something plus something plus something plus something 16 times. But fortunately, many of those 16 terms get a 0 in front, so you don't have to worry about those. You don't add them. It's 0 times that number, that's 0. So how many terms are you left with? Knowing that every single combination gets multiplied by one of these numbers, 16 in total. 4. Should we go with 4? Okay. Okay. All right. Let's do it. So I really only have to worry about those numbers because the other ones get multiplied by 0. You don't have to worry about those. Here's the cool thing. This is 0, 0. Yes, as in mu 0, mu 0. And according to the summation, you have to multiply them with x0, x another 0. Otherwise known as t. But you have 2 of those, that's t squared. With this minus in front. There you go. Let's also do the next one. Of all those 16 numbers, many of them are 0, but this one is not. You get 1 times the 1, 1. Mu is 1, nu is 1 combination. Because that's this one, that's 1. And 1, 1 means x times x. Plus 1 times x times x plus the x squared. Plus dy squared plus dz squared, yes? can see I already immediately went into my CS1 convention here. Squeeze it back in if you want. But is this familiar to you, this expression? Do we know something about this expression? That's invariant. That was what we found in week 2. So all of this notation, all of that is just to replace what we already knew in week 2 in this new notation here. Why go through all the trouble? I'm going to make the trouble even worse. We're so used to doing this in relativity that we don't even write down the summation sign. This is us being lazy. Just like we don't write down the C because it's there. We also don't write the summation sign. We say it's summed. Okay? So but we do have something now. We have what we already knew, and we know is invariant, can be written in this new way, with this Minkowski tensor in between. We also know that if you would transform this, and how do you transform? Well, by squeezing a Lorentz matrix in, that you will still get the same number. That's the invariance that we proved in week 2. So in relativity, when people like Brecht and me do it, we only write down this sort of stuff. We never write down all the components individually in full Lorentz transforms. We just do everything using this new notation. It's extremely economic. It takes only a very short amount of space, but there's more to it too. No, really, I mean, suppose that this was not zeros. You have 16 numbers. You have to do a lot of writing, yes? But that's not the main reason why we do this. Here's the main reason. Remember last week that we had a catalog of numbers that were in themselves invariant? Do you remember what they were? There were a bunch of them. Mass, speed of light, d tau. Yes. And we could use that to turn the Minkowski line element, this guy, into other objects. And those other objects, because the only thing we did with them was use invariance, had the same mathematical rules as the original Minkowski line element. That's what you get if you take a rule that's invariant and only do invariant stuff to it. Whatever comes out is still invariant. And one of the ones that we had is that we found this combination that E over C, Px, Py, and Pz also had Lorentz transforms between them. Because we got these 4 numbers out of those numbers. We did that last week. So that means that these can also be written with the Greek index on top and have exactly the same rules. This one is called P mu. The symbol is usually the spatial part. And the spatial part of energy is momentum. So this is P mu. And if you now, knowing that this follows from that, and it's equally invariant and placed by the same rules, then you know that this combination is also invariant. Yes? Please do yourself a favor and write out this. Remember, there's a double summation here. But since Minkowski matrix is very simple, minus 1, 1, 1, there's only 4 terms you have to take into account. Any guesses what will happen if you plug this guy in, write out all the summations, what the equation will come out? Is it pointing or is it finger up?
That's a question.
Okay, please, question.
Is there a special name for this invariant, or just?
No, that's just an invariant. But there is a special name, and this is that I think is important to note. Remember, I called this a 4 vector in between, and I mentioned it's not a 4 vector because it's 4 numbers in a column. It's 4 numbers that have this property together, or that have Lorentz matrix if you go to another inertial system. My question still stands. What happens if you now write out this combination? I mean, the outcome is invariant. We know that immediately. But which equation will come out, do you think? It's all something with an E and a P, maybe? It's this one. What you will find if you write this out is minus E squared over C squared. Remember, you're going to take the minus version of the zeroth component of the P, and the zeroth component of the P is E over C. And you have to multiply it with the 0, 0 part of the Minkowski. That's -1. So you're going to get minus μ squared over c squared plus all the p-values squared with plus 1s in front. Together makes up this. Is that invariant?
Yeah.
Well, yes. Because p squared with p to the other side is equal to m squared c to the 4. And we already showed last week that that is an invariant. So this equation, that it is invariant, it's a little bit more. It's not just invariant, we know the invariant. It's that invariant. It's m squared c squared. M squared c to the 4. M squared c to the 4.
Negative?
Yeah, maybe there's a minus r or c missing, but being a little quick due to time. But the key message here is this. If you can find, in whatever theory of physics that you're working on, a number, or a set of numbers, 4 numbers, that can be derived from this one, by using only c's and m's or what have you, then you know whatever comes out, the new 4 vector, p in my example here, will have exactly this rule. Always. So, let's call that object, this new vector that you might have found in your whatever physics you're interested in, let's call that one A mu. I'm being abstract now, right? Here we knew what they were, time and position. Here we knew what they were, energy and momentum. But if you find in whatever physics you're interested in, you find 4 numbers that can be related back to that one via C's and M's and d tau, so on and so forth, then you know that this guy plays by exactly the same rules as this guy, as that guy. You can create an invariant. Yes? Long story short, if you have found for yourself an A and a B, whatever physics they are, and they play by this rule, then you know that this combination is an invariant in special relativity. And this number is always the same in our inertial systems. And this is the key to creating invariant actions in whatever field of physics. Because if we now have a trick to turn our physics, whatever it is, back into invariant numbers. And if you have invariant numbers, you can create invariant actions. And if you have invariant actions, then all of this tells you the resulting physics that holds in every inertial system. And that's how we do it. If you allow me one more minute, I'll give one example of how people do this in particle physics, for instance. Some people I know of you follow particle physics. So Marcel and their friends work with these Lagrangians. Yes? They're curly because of reasons that have to do with quantum mechanics. I'm going to write down a Lagrangian. If you don't recognize this, because you're not following particle physics, don't worry. The point still stands. Here's a quantum field. Phi tells you where particles are, the particles that Jaco and Katie worry about in their research. Yes. You can prove this is a derivative of that field, because you can take a space and time derivative, and you can prove that this derivative taking is a 4 vector. It has that property. So knowing that that's the case, you have to prove it separately, but knowing that a derivative of a quantum field, this guy, can be written out in that way with the Greek index with the 4 numbers. Knowing that that's the case, it's a 4 vector. What do you know immediately about this combination? Even if you're not a particle physicist. It's invariant. Because what we found here is that this combination is always invariant. So when people creating particle physics and they wanted their quantum mechanics to work in every inertial system, they rejoiced in happiness when they found that derivatives of quantum fields behave according to that rule, because they immediately knew then this is the way to make an invariant. So we can create an action and we can create now particle physics, quantum mechanics in every inertial system. So, it took me a while because I had to introduce all kinds of new notation, but I hope that the payoff is great. If you find yourself creating a new theory of physics, first thing you do is look for 4 vectors. 4 numbers collected together that has these properties. If you found those numbers, then without thinking invariance, your whole theory is all the same, works in every inertial system. And that's, not in this course, but that's in other courses, how people create their invariant theories that work for all of special relativity. So, this is sort of my bonus to everybody, because the Binas formulas that we used before only work for Lorentz forces or just in one inertial frame, but here's a trick to make it work always for every case. Okay, and with that, let's go to the tutorial.